The Vision Transformer (VIT) model has demonstrated remarkable performance in vision tasks by dividing images into fixed-size patches and utilizing a learnable class token for image classification. However, it often requires substantial data and longer training times due to the computational demands of its attention mechanism. In contrast, convolutional neural networks, CNNs, possess inherent inductive bias through local filters, making them more efficient and quicker to converge with less data. This work proposes integrating a lightweight depth-wise convolution module as a shortcut in VIT models to capture both local and global information efficiently. The proposed approach employs depth-wise convolutions to capture local information, while transformer blocks are used to capture global information. The depth-wise convolutions serve as a shortcut, bypassing the entire transformer block, and the final combination is achieved through summation, providing a unified representation of both. This design ensures a flexible and dynamic integration of local and global features, achieving superior performance improvement with minimal additional parameters and computations. Two architectural variants are introduced. One aims to reduce parameters and floating point operations, flops, by utilizing the depth-wise module to bypass multiple transformer blocks, while the other seeks to improve performance by incorporating multiple independent parallel depth-wise modules. This approach demonstrates that certain modules are dispensable when training transformer models on small datasets, and by applying the approach without these modules, both parameters and flops can be reduced, while significantly enhancing performance. The proposed method addresses the limitations of VIT models by leveraging the strengths of CNNs while maintaining the global context capture capabilities of transformers. This approach significantly boosts the performance of VIT models on image classification, object detection, and instance segmentation tasks, especially on small datasets such as CIFAR10, CIFAR100, Tiny-ImageNet, and ImageNet. This research builds upon existing vision transformer models, such as VIT, DAT, and CATE, and hierarchical vision transformer architectures, addressing the limitation of relying solely on global views by integrating convolutional and transformer blocks. The integration of convolutional networks into vision transformers has led to the development of various hybrid models, such as CVT, botnet, and local VIT, aiming to leverage the strengths of both architectures. However, some of these models may require significant computational overhead or may not be lightweight enough for efficient integration. The pioneering Vision Transformer (VIT) model, introduced by Dosevitsky et al. In 2020, applies transformers to vision tasks by splitting images into patches and tokenizing them. Despite its effectiveness, VIT models often overlook the inductive bias inherent in images, leading to slow convergence and requiring more training iterations and large datasets. To address this limitation, a lightweight approach using depth-wise convolutions, DW-Conva, is proposed to efficiently integrate transformer blocks and convolutions with minimal computational overhead. The proposed architecture integrates DW-Conva into Vision Transformer (VIT) models, allowing it to capture local details that may be missed by the transformer. The DW-Conva module bypasses the entire transformer block, reshaping 1D image patch tokens to 2D feature maps, applying batch normalization and JELU activation, and performing depth-wise convolution with a 3x3 kernel. The resulting 2D feature maps are then reshaped back to 1D patch tokens and added to the output of the transformer block. This approach demonstrates simplicity, effectiveness, and flexibility, unlike some hybrid models that design complex hybrid architectures. The proposed architecture variants, designed by modifying the base structure, help reduce the number of parameters and computational costs when working with vision transformers that have deeper layers. The use of depth-wise convolutions enables the model to capture fine details in images, lacking in VIT models, while maintaining a lightweight design. The proposed approach introduces a novel architecture variant for bypassing multiple transformer blocks in vision transformer models, utilizing a depth-wise, DW, convolution module to reduce parameters and computational costs. This module can bypass 2, 3, or 4 transformer blocks, and its flexibility allows it to be applied to most existing vision transformer models without modifying the multi-head self-attention (MHSA) and feed-forward network (FFN) modules. The DW-Conva module captures local information independently through parallel operations, enhancing the transformers with minimal overhead. A complexity analysis reveals that the proposed approach is a lightweight module that can be easily integrated into various vision transformer models, such as the VIT-Tiny model, with negligible increased parameters and computations compared to the backbone. The experimental evaluation on vanilla VIT, KATE, and SWIN transformer models demonstrates significant performance improvements, especially on small datasets like CIFAR10, CIFAR100, and Tiny-ImageNet. The models are also evaluated on the relatively large dataset ImageNet 1K and COCO for object detection and instance segmentation tasks. The experimental settings for the models include parameter settings, dimensions, and depths, with the AtomW optimizer used for 300 epochs and 20 epochs warm-up. The batch size for the three small datasets is 128, utilizing 4 NVIDIA P100 GPUs. The results illustrate the effectiveness and efficiency of the proposed approach, showcasing its potential to enhance vision transformer models with minimal overhead. Here is the combined summary. Experimental results on small datasets demonstrate the effectiveness of the proposed approach in improving the performance of vision transformers, VIT, and KATE models. Removing positional embeddings, PE, significantly deteriorates performance, highlighting its importance in VIT models. However, applying the proposed approach to VIT models achieves substantial improvement, regardless of PE presence. Ablation studies on VIT-Tiny reveal that using kernel sizes of 3 or 5, or a combination of both, achieves the best performance. The proposed approach also improves KATE models, even without PE or layer scale and talking heads attention. The dynamic window convolution, DW-Conva, module is applied to various transformer-based architectures, including KATE and SWIN transformer. Bypassing different blocks in Chi-TXX's 12 with DW-Conva modules shows that accuracy drops when more blocks are supervised, but remains higher than the original models. This variant is suitable for deeper layers to reduce parameters and flops while maintaining accuracy. The SWIN transformer architecture is also evaluated, with the shifted window approach having minimal effect on performance. However, the SWIN-Tiny model with the proposed DW-Conva module achieves significantly higher accuracy than the original model with negligible parameter overhead. Visualization using GRADCAM reveals that transformer models exhibit global views of images, overlooking local information. In contrast, the proposed method captures both global and local information, enhancing each other and improving performance. The convergence of the proposed approach is significantly faster than the original models, reaching similar accuracy at around or less than 100 epochs. The effectiveness of the proposed method is further verified on the large dataset ImageNet 1K, demonstrating improved classification performance. The authors propose a novel approach to enhance the performance of vision transformers, VIT, and SWIN transformers on image classification tasks. GradCam visualizations, as shown in Figure 4, demonstrate that the proposed method captures both local details and global views, particularly for small objects. The experimental setup involves training on ImageNet 1K with a batch size of 1024 and a base learning rate of 1E3 using 8 NVIDIA V100 GPUs. The authors utilize KATE and SWIN transformer models, applying their method to each transformer block with a kernel size of 3x3 and incorporating a Depth-Wise Convolution, DW-Conva, module. The results, presented in Table 6, demonstrate a performance boost of up to 2% on ImageNet 1K. In comparison to convolutional counterparts like ResNet, the proposed approach achieves superior performance with minimal parameter and flops overhead. The authors also introduce a new class of models called KATE, which leverages class attention to improve the efficiency and accuracy of transformer-based architectures. Experiments on ImageNet 1K demonstrate that Chi-TXX's 12 and Chi-TXX's 24 outperform their original counterparts, achieving higher accuracy with significantly faster convergence speed. The proposed approach is also applied to object detection and instance segmentation tasks using the COCO dataset. Table 7 presents the results for mask RCNN and cascade mask RCNN with and without the proposed approach, showing improved performance in terms of map, AP50, and AP75. The experimental settings, including the use of Atom W optimizer, warm-up iterations, and learning rate adjustments, are also discussed. The results highlight the effectiveness of the proposed method in improving the performance and convergence of vision transformers and SWIN transformers. Here is the combined summary. This research proposes a novel approach to enhance the performance of vision transformer models by integrating depth-wise convolution (DW-conv) modules, which bypass the entire transformer block, capturing both global and local information with minimal overhead. Experimental results demonstrate that small transformer models equipped with this method outperform larger models with significantly more parameters and flops on small datasets for image classification, object detection, and instance segmentation when trained from scratch. The DW-conv module complements the limitation of vision transformers in capturing fine detailed information, crucial for object detection and instance segmentation tasks. Visualization results in Figure 7 illustrate the improvement in detecting small objects and predicting accurate boundaries using the proposed approach with mask RCNN. Analysis indicates that the approach not only enhances accuracy but also enables faster convergence rates for image classification, particularly on relatively small datasets. The method can significantly enhance small-size transformer models, even surpassing large-size original models in terms of performance on small datasets. However, the improvement may not be as pronounced when the dataset is relatively large, or for transfer learning due to pre-trained models already possessing substantial representation ability. Several architecture variants are introduced, tailored to different models and objectives, anticipating further research on vision transformers, particularly in the context of small datasets. The work builds upon various contributions to vision transformers, including attention mechanisms, application to image recognition, and efficient convolutional neural networks. The authors also acknowledge related works on applying vision transformers to various tasks, such as point cloud completion, audio-visual crowd counting, and image transformers with attention-based distillation. Vision transformers have made significant progress in recent years, bridging the gap between convolutional neural networks, CNNs, and transformers. Various architectural innovations have been proposed, including the MSG transformer, which leverages messenger tokens to enhance spatial attention, and the twins architecture, which introduces an adaptive spatial attention mechanism. The shuffle transformer rethinks spatial shuffle operations, while the CVT model incorporates convolutions into vision transformers. Bottleneck transformers offer an efficient alternative to traditional transformer architectures. These advancements have been applied to diverse applications, such as wetland mapping, salient object detection in optical remote sensing imagery, and scene understanding from aerial imagery. Models like Wet Map Former, Hybrid Feature Aligned Network, HFA-net, and Local Global Coordination with Transformers, LGCT, demonstrate improved performance by integrating CNNs and transformers. Furthermore, various techniques and architectures in deep learning have contributed to the development of vision transformers. Layer normalization, Gaussian error linear units, GELUS, and batch normalization are widely used techniques for stabilizing training and improving model performance. Benchmarks like the Tiny-ImageNet dataset, ImageNet Large-Scale Visual Recognition Challenge, ILSVRC, and Microsoft COCO dataset have been instrumental in evaluating the performance of deep learning models. Optimization algorithms like ADAM, techniques like auto-augment, random erasing, and mix-up, and architectures like MIDI-DETR, VisFormer, and ResNet have also played a crucial role in advancing vision transformers. Conditional positional encodings, GRAD-CAM, and squeeze and excitation network, SENET, are additional techniques that have improved the performance and interpretability of vision transformers. The referenced papers by He et al. 57, and Kai et al. 58, significantly contribute to the field of object detection in computer vision. He et al.'s mask RCNN 57 extends the faster RCNN architecture by incorporating a segmentation branch, enabling the model to predict pixel masks for object instances. This innovation enhances object detection and segmentation accuracy, particularly for objects with complex boundaries. Kai et al.'s Cascade RCNN 58, builds upon the faster RCNN architecture, introducing a cascaded detection framework that iteratively refines object proposals and classification scores. This approach allows the model to focus on high-quality object detection, achieving state-of-the-art performance on various benchmark datasets. Both papers employ a region-based convolutional neural network, RCNN, architecture, which generates region proposals and classifies each proposal using a neural network. He et al.'s mask RCNN adds a segmentation branch comprising a fully convolutional network, FCN, that predicts pixel masks for object instances. Kai et al.'s Cascade RCNN introduces a cascaded detection framework that refines object proposals and classification scores through multiple stages. The mathematical formulation of both approaches relies on the intersection over union (IOU) metric, measuring the overlap between predicted and ground truth bounding boxes. He et al.'s mask RCNN uses the IOU metric to train the segmentation branch, while Kai et al.'s Cascade RCNN employs a cascade of IOU thresholds to refine object proposals and classification scores. Experimental results presented in both papers demonstrate the effectiveness of these approaches in object detection and segmentation tasks. He et al.'s mask RCNN achieves state-of-the-art performance on various benchmark datasets, including the COCO dataset. Kai et al.'s Cascade RCNN also achieves competitive results on the COCO dataset, outperforming other state-of-the-art object detection models. The flow of ideas between the two papers is evident, as both build upon the RCNN architecture and employ similar mathematical formulations. However, each paper introduces novel ideas and methodologies that advance object detection and segmentation research.